Okay, so let me start with a little recap of last time. So we are discussing simplicial complexes. So a simplicial complex for us, we'll think of it as a subset of the power set of some set V, which is the set of vertices. So elements of K are simplices of some dimension. So for example, graphs fit into this setup. So a graph, you have some V vertex set, and then G, if you think about it as a subset of the power set of V, these are subsets of size at most 2. So there's only vertices and edges, in other words. If there's only vertices and edges, then what you have is a graph, or at least the geometric realization of G is a graph system. All right. Okay, so last time at the end, we defined, so given K and P a vertex, we have the edge group which is consists of edge loops based at P up to some equivalence. So for example, yeah, so let's take V, let's take K, well, okay, I'll write this all out. K is the power set of V minus the empty set. So this gives us the geometric realization looks something like this. We have 3 vertices, and we include all of the possible simplices. So you just get a 2-simplex or a disk, topologically a closed disk. And let's call this P, the base point, 0. So the edge group in this case, well, it contains things like, so an edge path, remember, is just a sequence of vertices. So we have like, and we want to start and end at P, so which is 0. So we have things like 1, 2, 0, 1, 2, 0. The equivalence class of this, that's an element of the edge group. There's other things we could do. We could go the other way, 0, 2, 1, 0. Or we can do things like 0, 1, 0, 1, 0. These, so note though that, well, these are all equivalent to, or they define the same element as the constant path. So for example, 0, 1, 2, 0, this is equivalent to, well, let's see, so 0, 1, 2 bounds a triangle. So there's this move where we can just replace this with 0, 2, 0. And then this is equivalent, since there's backtracking, you just go 0, 2, 0, this is equivalent to 0. Okay. So as you would expect in this example, the edge group is actually trivial. And the edge group is supposed to be a combinatorial version of the fundamental group. And we already know that the fundamental group of a disk is trivial. And so you'd expect the same for the edge group. And well, okay, so we'll see this shortly. So, right, so the main thing for today is to give a method for giving, well, okay, sorry. So the main thing for today is to give a presentation for the edge group. All right, so the way this is going to work, so let's assume that K is connected, which is to say any vertices U and V are connected by an edge path. And let's write, so, okay, so let's write, it'll be convenient to write the vertex set, the vertices as V naught up to V, or let me just say as VIs, like this. And let's choose a maximal tree, L, in K. So this is a subset of just the vertices and edges of K, which give a graph, and it's a tree, so it contains, so there's no loops in it, and it contains its maximal, which is to say that it contains every vertex. So let me just say this was something we discussed a little bit at the beginning of the course, and you prove that a graph has a maximal tree on homework 1. Okay, so now we're going to define a new group which we'll define by a presentation, which is to say to give generators and relations. So the generators are going to be Gij for each edge, Vi, Vj, with I less than j. Okay, so this group, it has a generator for each edge of the simplicial complex, and the relations. So there's 2 types of relations. So the first one is Gij, Gjk is equal to Gik if Vi, Vj, and Vk is a simplex in K. And then the second relation here, I should be less than j, less than k. And then the second relation is that Gij is trivial if the edge spanned by Vi and Vj is in L. Okay, and then, well, the theorem is that GKL is isomorphic to EKP. Okay, so I just defined this this group in this way, and the claim is that this actually gives a presentation for the edge group based at some point. So let's see an example of this. So let's take this simplicial complex. And let's take the, yeah, okay. So let's write down the group G, K, L in this case. So we need to choose L, and there are various choices. So it's just supposed to be a tree, contains every vertex. So this is an example. There are other things we could have chosen, but so now what do we get? So we get generators. So there's one for every edge. So there's like G01, G03, G12, and G13, and G23. These are all the edges. And then we have relations. So there's this triangle gives a relation. G12, G23 is G13. And then the other type of relation is that we just set equal to 1 anything which belongs to this maximal tree L. So in particular, so then G01 is 1, G03 is 1, G23 is 1. Okay, so now let's think about what group this defines. And before we do that, let's first think about what we expect the answer to be. So here, the geometric realization of K, well, so we have this, well, yeah, so let me just say in words, the geometric realization of K is, it's topologically, or it's not topologically equivalent, but it's homotopy equivalent to the circle. Just because, well, you can sort of collapse this triangle to this edge, and that defines a homotopy equivalence. And so then the fundamental group of the geometric realization is the same as the fundamental group of the circle, since the fundamental group is a homotopy invariant. And we know the fundamental group of the circle is Z. So this is the answer that we expect to get. So let's see about this. So first of all, each of these relations tells us that we don't need, right, so we start out with this presentation. We have these generators, well, yeah. And then we have these relations. So this defines a certain group. And we can simplify this presentation to try to understand what group we actually get. So whenever a generator is equal to 1, well, that just says there's no point in including that in your generating set. So we can just remove these generators here. And then, well, now let's look at this last relation. So we already know that G23 is 1. So this is just saying that G12 is equal to G23. So the group defined by this is isomorphic to the group where we just have a single generator and no relation. And that group is exactly the integers. Okay, so this is G, K, L. Okay, so some comments. So we'll prove this theorem next time, but for now, I just want to see some examples and make some remarks. So a remark is that the theorem gives a reasonable way to compute the fundamental group if X has a triangulation. X is topologically equivalent to the geometric realization of some simplicial complex. Since then we know the fundamental group of X is isomorphic to the fundamental group of the geometric realization, which is isomorphic to the edge group with some base point, which is isomorphic to this group GKL that we just defined. So these isomorphisms here, these still require proof, which we'll discuss. But then this last thing, this comes to us with an explicit presentation. So this is a group that's defined in terms of generators and relations. So this is how one can write a presentation for a space with a triangulation. So let's actually see this in some examples. Let's do an example here. So let's take a triangulation of the circle, and well, yeah, so I guess this is similar to the example we just did. Let me do this kind of quickly. So let's take this triangulation, vertices 1, 2, 3. So then in this case, GKL, so we pick some maximal tree, and that's L, and we have generators G1, 2, G2, let's say 1, 3, and G2, 3. And the relations, G1, 3 is 1, which is also G2, 3, and then G1, 2, G2, 3. Oh no, that's it. No, sorry, that's it. There's no faces, so this is the only relation. And again, this is G1, 2 with no relations, so that's Z. So notice how quick that was compared to how long it took us to prove the fundamental group of the circle is Z last week. But of course, it's not super quick because it's going to take us a lot of work to prove these theorems. But at the end of the day, once you know these theorems, this is a quick way to do some computations. Let's do a different example. Now let's take a triangulation of the two-sphere. And let's specifically take the surface of a tetrahedron. So let's call vertices 1, 2, 3, 4. So we know what we should get as an answer. This group, since it's the fundamental group of the sphere, should be trivial. So let's just see if that's indeed the case. And this is good practice in working with this group. So here we have generators. There are 6 of them for all the edges in the graph. And then we have relations. So there are a bunch of relations coming from the triangles. There are 4 of those. So G1, 2, G2, 3 is G1, 3. G1, 2, G2, 4 is G1, 4. G1, 3, G3, 4 is G1, 4. G2, 2, 3, G3, 4 is G2, 4. And then there are other relations coming from the maximal tree, which we haven't chosen yet. Let's choose the maximal tree to be this one here. And so we just need to set all of those vertices to the corresponding generators to be trivial. So that's G14 is 1, G24 is 1, and G34 is 1. Okay, so now let's think about what group this describes. So these relations all say that we don't need any of these generators. And now let's work through, okay, so that simplifies these relations here. So let me just remove any instance of these words, or these generators, G14, G24, G34. I guess that's all of them. And so then now these relations simplify. So here, this tells us that G23 is trivial. That's what this equation then tells us. So let me maybe do this in a different color. So we learned that's trivial. G13 also is trivial. G12 is also trivial. And then that's it. So now we have, so this tells us that GKL is the group with no generators and no relations, which is just the trivial group. Okay. One more example. Yeah, let's do one more example. Let's take a space, a triangulation of the wedge of two circles. So K is going to be this simplicial complex. All right, and now let's see what we get for GKL. So let me first start by picking L to be this tree. So now we have generators. Well, okay, so let's just write them out. So a lot of these we can already see are going to disappear. According to our relations, but okay, so here are the generators. And then we have relations. Well, there's no faces, there's no triangles, so the only relations are the ones coming from setting generators that correspond to edges in the maximal tree to be trivial. So, okay, so G01 is 1, which is G02, and G03, and G04. Okay, so this is what we compute, and what we're left with at the end is that this group has a presentation with two generators and no relations. So we say, so some terminology, a group with no relations is called a free group. So the elements of this group are just like words in these two generators. We could just call them A and B instead. So elements of here are just words. You know, you have in A and B inverse. And the operation, you just concatenate them. You concatenate words. Okay, and that's like saying, yeah. So in this group, the fundamental group, you have of a wedge of two circles. The different loops up to homotopy just come from doing some word. You have going along A and going along B, and you just do some word, and that gives you an element of the fundamental group. Where here, like this word, you do A, and then you do B, and then you do A backwards, and then B twice, and then A backwards 7 times, and then B, and that gives you an element in the fundamental group. And well, this computation, combining with all the theorems, some of which we haven't proved here, says that this gives exactly what the fundamental group of wedge of two circles is. It's, you just do all the different words. Okay. Let me mention one more. No. So now let me move on and finish with a few remarks. So an observation. So note that, let me just say this as a couple of different remarks. So first, GKL, this doesn't use any info about simplices of K of dimension greater or equal to 3. We only use vertices, edges, and faces. Okay, so well, this is a useful observation. I mean, here in defining this group, the only data that we used was things about edges and triangles in the simplicial complex. Okay, so that's a remark. Another remark. Well, it can be tedious to write down this group, GKL, if K has many simplices. Well, okay, we'll see. I mean, even here, like, look, this group turned out to be the trivial group, but we had to write down all this stuff just to see that the group was trivial. And here there's a relatively small number of simplices, but even, yeah. So it can get a lot worse than that, as maybe we'll see in some examples later. Another remark is that what else do I want to say? Well, maybe the thing to say is this. The presentation for GKL is often very redundant, which is part of what makes it so tedious. And this is actually a problem in terms of, so you have this group presentation and it's redundant. A lot of the generators maybe aren't actually necessary. So the reason why this is problematic is the following. So there doesn't exist an algorithm to decide if two presentations in terms of generators and relations, generators are usually called S and relations are R. Let's do it that way. So we say we have some other generating set and some other relations. In general, you can't decide if these define isomorphic groups. So for example, you can't decide in general if a given presentation is the trivial group. Okay, so this is actually maybe a bit worrying because so I gave you this definition of this group, and I said, well, this computes the edge group, and I said, well, this does exactly what we want, but it's actually maybe a little disheartening because you might write down this presentation, but then not be able to decide if the group that you get is trivial or not. So in what sense does this actually give you a computation? Right. And well, another remark related to this is well, for different choices of L, we get L a maximal tree. We get different presentations. You know, you have GKL and GKL prime. And it's not at all clear that these define isomorphic groups. I mean, it's the same sort of problem. You have two different presentations of some group, and are they the same group? And so group theoretically, that's not an easy thing to decide. But of course, well, we are going to show that different choices of L define the same group. And that's part of the content of this theorem. Because, of course, the left-hand side doesn't know or care anything about the particular L you choose. So for any L you choose, it's isomorphic to the edge group. So in fact, the choice of L doesn't matter. Okay. So I think we'll stop there. And next time, yeah, we'll prove this theorem here.